So thanks everyone for coming along today. I'm going to be giving a little bit of an overview of TC Flower, what it is, why it is, what people are doing with it. I'm with Netronome. We make smart NICs, so there'll be an element of hardware offload to this talk as well. All right. So basically what TC Flower allows you to do is to construct a match action data path. So these days we have XDP and so on, and this provides a different paradigm which allows you to do fully programmable packet processing. But nonetheless, a bit slightly older style match action data paths are still quite useful and quite widely used, I believe. So I'll be talking about those today. And so what is a match action data path? What do we mean? So your packet comes into the system about here, and some kind of classification takes place. So typically this involves some code running through the packet, examining headers, populating some kind of key structure, maybe selectively, or maybe it runs through the whole header depending on the implementation. It may also take into account metadata that may be somehow attached to the packet. So for example, the input port, you usually know that, but you may also know other things. Say it was previously tunneled and it's been decapsulated. There may be some information about the tunnel outer header available as metadata, and you may want to add that to the key as well. So then once you've got your key set up, you do a lookup in your flow rules, which are usually pre-populated somehow. And then if you got a match, then you get a bunch of actions. And the actions could be something like drop, it could be output, it could be something slightly more complicated like add a VLAN, but usually at the end you either drop or output. And then from there, another action, you meant forward to another table. So from the match to the action, you may go back and do another set of matches. And that's what a match action data path is. So TC Flower allows us to construct these kind of things. So TC Flower is the match part of it. So it implements the classification as I described just a moment ago. It allows us to classify quite a wide range of fields. So of course L2 fields, a MAC address and so on, VLANs, MPLS, moving a little further up the stack, IP addresses, and even to a limited extent, L4 things like UDP and TCP ports. Also tunnel metadata, so the tunnel ID is I guess the most obvious example, but also things like the outer IP addresses and so on, you can match on them. And the input port, although this not strictly necessary at this point because the rule's always attached to a port. And then we have TC actions. Now these have been around for quite some time. They get constantly updated and improved and expanded on. So we have pedit, which is the go-to tool if you want to modify the packet data. So if you wanted to modify one of the addresses at any layer, or one of the ports, or really any other part of the packet you can think of. We have merd, which is a slightly non-obviously named output action. And we also have VLAN action. There's others, but these are maybe the most interesting in the context of this talk. Okay. So here's an example of TC Flower in action. So those familiar with TC will make more sense of this than those who aren't. But basically, firstly, we establish a QDisc on the ingress rule, which is basically allows us to attach our Flower rules to something. And then the filter, we're adding it to E0. It's going to be IP protocol. The parent is the root, so it's the topmost node. And then here we are getting into Flower land. We're going to use the Flower classifier to deal with this packet that we've selected. We already know that it's IP, but we want the IP protocol to be SCTP, and then the destination port to be port 80. And if those conditions are true, then we drop the packet. So this example is completely arbitrary. it could be UDP instead of TCP. We could not match on the port. We could match on the IP address. We could not drop the packet. We could output it. It's just an example. Okay, so I talk briefly about the implementation of Flower. Maybe one or two little quirks in it. So firstly, it makes use of this subsystem in the networking stack called the flow dissector, which is shared by various other things. So this is the same piece of code that generates the hash for RSS and so on. It's used in a slightly different way in TC Flower, and I think it was decided in the last few days that this behavior will be broken up a little bit, but it will still be part of the flow dissector. In the way the flow dissector works in general is you describe which parts of the packet you're interested in. So I can't remember the exact details off the top of my head, but for example, if you might say I want to dissect IP addresses, and I want to dissect, but I'm not interested at all in UDP ports, layer 4 ports, so that you would set up the description to say, please do IP, but don't do layer 4. And the section will only examine the packet as described by the request. And the flow dissector, when it's extracting the data from the packet, it seeds it into a data structure. And then essentially that data structure is returned to the caller. So in the case of Flower, that resulting data structure is then masked. So a simple example of masking might be that instead of matching on an individual IP address, you want to match in all IP addresses in a particular subnet. So we can use masking to achieve that. And then the resulting masked key is then looked up in some kind of hash data structure. And if there's a match, the actions are executed, and these are TC actions. If there's no match, then processing continues as per the usual TC rules. So it will basically look for the next classifier, and if there's no more classifiers, it will fall down through to the regular Linux stack. So one thing to observe about the current implementation, and it's not really a limitation in the design as such, but currently you can only have one mask at a given priority level. So this means that all the matching going on at a given priority level has the same mask. But if your rule set has different masks, so say you have one set of rules that is matching on IP addresses and a different set of rules which is matching on IP addresses and ports, then you would have to do these at a different priority level. And it's up to the caller, the user space, who programs the rules, to arrange the priority levels correctly. So if you have disjoint flows, by disjoint I mean that regardless of what the mask is, that no two flows can match the same packet, then the ordering of the flows in terms of the priority levels is unimportant from a correctness point of view. But if you have overlapping flows for some reason, then you need to arrange them such that the ones you want hit first are considered first. But a common use case for this is to use it in conjunction with OVS. And in that case, the flows are always disjoint. So the ordering is not so important. Okay. So one of the things that we can do with this is, in a sense, TC has two halves. There's a control plane and the data path. And up until recently, the data path and the control plane are both in software. But we can now use this same software, this same control plane, to configure a data path in hardware. The data path in software is still there, and any functionality that exists in hardware is also implemented in software. So it should be, you should get the same behaviors. It's just a question of performance. But working for a hardware offload-oriented company, why would you want to offload? The reasons are usually twofold. One or both of the reasons one or both of the following two considerations: is to give greater throughput or to reduce the CPU utilization. So once we get to high packet rates that you might see, say on 10 gigabit or above networks, it can consume a lot of host CPU to process these packets. If we push these to the hardware, then the host CPU becomes free for other use. Something like that. So a quick history of TC hardware offload, and most of the credit here goes to John Fosterbent, who is somewhere around here today. So I was very surprised to find that the history goes way, way back to 2639, which is about 6 years ago, I think. And it was first added to MQ Prio. So this is just a queuing discipline. You can't use it to construct data paths and so on, like I just described. But you can use it to program certain behavior into the hardware regarding on how it queues packets. It's been around for a long time. And at that time, this NDO setup TC was introduced. And the relevance to that, to what I'm talking today, is it's the same NDO that we're using to offload TC today. So in 4.6, so this is going back about 18 months ago now, John added support for the U32 classifier offload. Now U32 functions quite differently to Flower, but it's conceptually similar in the sense that a packet comes into the system and it can match on it using some kind of user configured parameters. So skipping forwards to not quite the present, but the present as of when I prepared the materials for this for today. 415 RC4. I don't think there's been. Sorry? Yeah. See, I made a mistake. This is in the future, but what I mean is 414 RC4. So basically a month ago, and the feature set shouldn't have changed since then in terms of what's going to be included in 414. So the following classifiers, BPF, Flower, Matchall, all support some kind of offload, or offload is implemented for all of these in some places. And of course, the MQ Prio continues to be supported. I just give a particular shout out to the people I work with. Netronome, we're supporting both the BPF and Flower classifier. Just a quick word about the actions. So this history here refers to basically when the hook was added or when support was added for offloading one classifier or another. But what about the actions? Well, the actions, the way the TC works is the actions are attached to your classifier. So we don't need an extra hook or so on to offload the action. You just get the bundle, the flow, the rule, whatever you want to call it, of information coming down to the driver, which implements this NDO. And then the driver can examine, firstly, the classifier and all the information in the classifier, but then it gets the actions. And for all of these, all elements of the rule, it can decide whether or not it wants to offload it or not. So it may choose to reject. So for instance, the Netronome driver, if it gets a request to offload the U32 classifier, which it doesn't support, it just rejects it. If it gets a request to offload something which it otherwise likes, but it's using an action it doesn't support yet, it rejects it. So this is I'll get a little bit more onto this flow in the following slides. Okay. So it's all very well to be able to program rules, and one possible approach to this would be to kind of do it transparently without the user knowing. So in that kind of scenario, if you had a box and then you plug in some new piece of hardware that gets offload, or you upgrade the kernel so it supports the offload, then suddenly, without changing the configuration, everything would go faster. That would be a transparent model. This is not the model that's supported. The model that's supported allows the user to control things, and generally speaking, to opt in. So firstly, the first level of configuration we have is a global on-off switch on a per device basis, a per Netdev basis, of whether or not you want to allow TC offload. So that would be for all types of all the different classifiers. So you can turn it on and off as per the example there. The next layer is, well, the other layer is a per flow configuration. So you may want to do some offloading of flows, but you may want to control the flow placement for some reason, any reason. So an example of a reason might be that you may have some hardware that can only support a limited number of flows, and you may want to place the more important ones for some evaluation of important into the hardware and leave the other ones into software. That would be one example. There are others. So to allow this policy to be selected by the user and reflected into hardware, we have two flags, skip hardware and skip software. So in the case of skip hardware, it just means don't add it to hardware, only add it to software. And if you can't add it to software, it's an error. And unsurprisingly, skip software is the opposite. It means don't add it to software, only add it to hardware. And if you can't do that, it's an error. And then you have the default policy, which is a bit undefined, but in practice what it is try to add it to hardware if the hardware is there. Regardless of what happens, add it to software. And only if it fails to be added to software, then you get an error. So this allows the placement of things. That's very nice. We can control where our flows are, but it's also be nice to be able to inspect where they are. So that's where these separate flags come in hardware and not in hardware. And these allow you to see where the flows are. So I'll just show a quick example. This is the same example as before, except the part in bold where I've said please skip hardware. So what I'm saying is that flow that I showed before, I want to only place that in hardware, which is ETH0. And if ETH0 doesn't support hardware offload, it's been turned off using ETH_tool, or for some reason this flow is not acceptable to the hardware, then I'll get an error. As it happens, I didn't. So here this is the same flow again. I'm just asking the kernel to tell me what it is. And what's been reported here is that I asked for skip software and that it is present in hardware. Well, in this case, if it wasn't present in hardware, it wouldn't be present at all. But it would be possible for, say I had not used the skip software flag, but I had added it to a device that supports offload, then I would see that it's in hardware, but it would also be in software because there would be no skip software flag. Okay. Okay, so I'm actually kind of getting towards the end of this presentation. So now I'd just like to talk briefly about some possible enhancements for this implementation. So one is just to extend the current static matching. So currently we can, for example, do op, but we can't do neighbor discovery. The main problem with adding this kind of stuff is it adds complexity to the flow dissector, and this can cause stuff to break for other people, or just in general makes the code more complex. It's also arguable that neighbor discovery and these kind of things aren't particularly good targets for offload, which is one of the motivations for Flower. But hopefully in the long run we can resolve these complexity issues somehow and allow these features to happen, so we can have a fuller implementation on the software side and more fully describe the data path, even if particular flows might not be good candidates for offloads. We support MPLS, label stack entry matching, which is kind of nice, but I noticed when I was looking through the code not so long ago that it's not maskable. This is kind of a trivial kind of update. Pretty much everything else that makes sense to mask can be masked, so I think that should be added. And then there's Geneva options. There are other types of tunnel options too, but in particular Geneva is interesting because things like Oven use Geneva, and they use options to more accurately identify, I think, the tenant. So this on the inside of the kernel, this is not so hard to implement because the tunnel options are already extracted. They're already available internally. The main question is the nice way to represent this to users. So for example, the first patch I sent not so long ago just exposes a bit mask, a byte mask. This is a byte string, sorry. This is not so great because this is this mask of bytes. You don't know what they mean. And the data does have structure, which is TOVs, so it would be a bit better to expose the TOVs. But then you come up with this issue of should you match them dependent of the order or independent of the order. I prefer for it to be order dependent because it's a bit nicer on the fast path. But regardless, I think we can add this, especially now that once we untangle a little bit from the flow dissector, and it won't have impact on other users. Okay, and if my memory serves me correctly, this is the last slide. So contract, this is a bit hot topic, and actually at the NetFilter workshop downstairs, they're probably talking about it right now. So everything Flower can do so far in terms of matching is stateless, in the sense that it's just derived from the packet it sees. There's no other information required. But in writing security policies and so on, it can be useful to have stateful information. So you can write your data path in some data path rules in some way that are security aware, and they perhaps don't allow new flows in one direction, only in the other direction, and so on. So this requires quite some discussion, and it's kind of incomplete. But what Open vSwitch does, which seems like it could be good inspiration in this area, is essentially you have your match. And you say, okay, well, my SCTP port 80 packets, just like the rule I had before, I want to do something with them, but I want to do something that's state dependent. Now I think of it, I'm not sure if that makes sense for SCTP, but let's say TCP port 80. And so my action is some kind of contract action. So the contract action would just feed the packet into the contract system, and then get some kind of state from contract subsystem out of it that says, you know, is this connection new? Is it related? Is it this kind of information? And then you go back to your match, your second match, which is different for this one. And this one will match, the match there would include some kind of information of the contract. So like, if it's new, drop. If it's connected, pass, or whatever. So that would be, what to do is described here. And then of course, as an ongoing theme of offload in my life, but also in this presentation, the idea would be to try to find some way to push that configuration down into the hardware. But also, of course, provide the software implementation, which would have to come first. But it is quite a sticky topic, I think. Well, not it's a difficult problem, which will require more discussion. Okay. As promised, that was the last slide. So thank you very much for your time. Any questions? Or so on? If not, please feel free to come up afterwards.
Simon, in your hardware, do you support changing the flow key on the fly, or the match fields, they are configurable, or you have like fixed matches that are, I can give an example, right? You were matching something like a 4-tuple TCP/IP source and dest address plus, the.
All right. So I think I know where you're going with this. Could I support in the hardware matching on, say, a particular value at a particular offset? No?
Yes, exactly. Yeah. And
so on the hardware,
configurable?
Yeah. So in the hardware side, yes, we could support. Well, it's a bit of a misleading thing. The Netronome hardware is fully programmable, so it's a question of does the firmware implement it? If it doesn't, it could simply be added. But I think actually it already does support it.
So right now, your driver can't support any random kind of matches. It's
so
like
so the driver can only do what the Flower does. Mm-hmm. And Flower doesn't support that particular thing. If Flower was to get it, the driver, I think it would be very easy for us to support that.
Thanks.
Anybody else?
Great. Thank you very much for your
Mm.
time, and enjoy
Thank
the
you.
rest of your week.